Okay, so number of questions. We're probably looking at 1 to 2 questions per experiment. Since there's 15 experiments, you're probably looking at about 30 questions. As far as the design of those questions, we've got 3 practice quizzes. I'm almost positive now I wrote this one. Practice quiz number 1, pretty sure it was written by me. So those are the types of questions that I ask, which you should look very, very familiar because they're very, very similar to any of the practice exams. Okay, or not practice exams, that's what they are. Group activities, the pre-labs, the in-labs. So it's, for the most part, reiterations of those exact same questions, okay, or variations thereof. For instance, this first one is looking at intermolecular forces. Okay. That particular semester, all of the slides or all of the recitation discussions were strictly focused on intermolecular forces. We talked about them a lot this semester, just not as much, but fully expect you to have those forces memorized and know what they are, and if given a structure, being able to identify what the intermolecular forces are possible for that individual structure. Okay. Because that's probably the only thing you're ever going to remember from this course. Okay, it's probably the only thing that's going to be particularly useful as well. None of you, more than likely, none of you are going to move into synthesis, so it doesn't make sense to have you memorize reagents or anything like that. So understanding what the primary forces are and a small application thereof is one of the primary goals. Your definitions of Bronsted-Lowry acids and bases, Lewis acids and bases, electrophiles and nucleophiles played a much smaller role this semester, but again, that's really, really, really important. You can fully expect to see questions asking you to define that. And I will probably leave them less or very little room for open-endedness. So in this case, it was just a circle. Okay, so a Bronsted-Lowry acid, first off, you hear Bronsted-Lowry and you should think hydrogen ions, also known as protons. So your very first thing when you see Bronsted-Lowry is to circle protons. If it's an acid, what's your favorite acid? And nobody? HCl. What does HCl do? Gives up H+. So it's a proton donor. Okay? Or it donates protons. Does that make sense? So if you have a couple examples for each of these, so your Bronsted-Lowry acids, see if this actually works. A good one would be HCl to remember, and when you think HCl, you should be thinking when I add that to water, I get H+ and Cl-. So what happened? HCl gave up a proton donor. Okay? If you've got that quick memorization tool at the back of your head, you can start to apply the definitions very, very quickly and derive them as you go. Okay, for instance, we could take that a step further and say HCl plus H2O. We just said HCl was a proton donor, so it's going to give up H+ to what? In this case, there's only 2 things written up there, right? HCl and water. So what would HCl have to give up that proton to? As a hint, it's not HCl. Water. So if you give the hydrogen to water, okay, you would be left with Cl- because you just lost H+, so it's got to be minus. What happened to the H2O? That's now H3O because we added a hydrogen to it. Okay, so if we looked at that, we could then go through and say we've got our Bronsted-Lowry acid because it donated a hydrogen. Well, the opposite of an acid is base, so water has to be a base in this reaction. You could look at the flow of electrons. HCl is giving up hydrogen ion. Oops, I didn't want to exit. I hate it when I do that. Okay. HCl gave up H+. So for H+ to interact with H2O, what does H2O have to supply? How do you cancel out the positive? With a negative. So our oxygen has to donate electrons. It's still a base, but if it's an electron donor, now we're looking at the electrons, not the hydrogen, we could go with Lewis. Okay, well, what do bases react with? Acids. And if we really wanted to force the definition, if we're going to look at the flow of electrons, we call it now a Lewis acid. So if you've got a strong acid or base in mind, add it to water and work through what you know to be true, or what hopefully you know from general chemistry, which is pretty much the only thing they should have taught you in general chemistry was basic acid-base reactions. They probably didn't, but that's what they should have done. Okay. Can I scroll here? I don't think I can scroll here.
With the glassware?
With glassware, I don't think I'm going to ask questions on glassware. Okay. Mainly because I wasn't in the lab to guarantee that you guys knew what glassware you were using when you used it. Okay. And because I can't guarantee that that just reiteration verbal punishment was occurring in lab, I can't really expect you to know too much of that. Okay. So we can ignore any kind of glassware questions. You'll notice most of them are fairly straightforward. You should be able to pick up, say, what this guy is, right? Erlenmeyer flask. Be able to pick up the one out on the far end. Got your conical vials. This one we ended up not using this semester. I don't think you used it this semester, so you wouldn't know that one. The first one you did use, but again, I don't have that connection or that tie to lab to guarantee that you guys covered that material the way you should have.
What is it?
It's an air condenser. Just making sure you were right.
Over here, not me.
Okay. So the other thing I want to pull up here, let's get the syllabus to make sure. Cover all the labs. So I can't, or I won't do glassware, but safety is important. Those should be fairly straightforward. I thought there was a safety question in one of these.
In the practice?
In the practice exams, yeah. There's one that's along the lines of the safety, so that's practice quiz number 3. The very first question, in fact, is looking at what you do with waste, which is ultimately a safety question. Okay, so there are the obvious safety questions: long pants, closed-toed shoes, goggles, that kind of fun stuff, gloves. But then you also get the waste questions. So if you measured out a bunch of HCl, okay, but then didn't use it, you should be able to tell me where exactly you put that. And that's partly what your practical was on too. So you had to summarize what waste you used and where you put it. Okay, so if you had unused HCl, where would you put it? To the acid waste. Where it gets tricky, which is questions I won't ask, is if that HCl had been a wash, say you did your extraction of it, okay, of an organic mixture. You now have some amounts of organic mixture in that HCl, but it's primarily HCl. Where should you put it? Organic. Really depends on who you talk to, but in most cases, aqueous waste can be neutralized, acid or base. The organic waste that you put into it, you can't neutralize that. That's stuck. So we might as well put that in a place where we know it can be disposed of properly. Okay. We then moved into let's see if there are other questions in here. Sorry for the fast scrolling. There's another one there. Hexane. Hexane is what kind of compound? Organic. This question is not one of my favorites because it gives you the name and you're expected to know the structure. That means a lot of nomenclature. I don't expect nomenclature. You can fully expect that if something was like this on the exam, you'd see the structure of hexane right next to it. Okay, so I'd give you some extra information. So based on the structure, you should be able to interpret if it's organic or not organic. How would you know it's organic? Carbon and hydrogen. Okay. more glassware we don't have to worry about. There's a safety one with goggles. Okay. After that, we did melting point. Okay. You'll see this question show up, and I believe all three of these to some extent or another. Where is it here? There it is. So you get, first off, the interpretation of what you see from a melting point. Okay, so if we take a look at this multiple choice question, an impurity affects the melting point in some following manner. You can expect some short answer explanations. You might see multiple choice like this as well. It depends on how much of a direct answer I think it is versus an explanation. Okay, so in this case, I personally wouldn't ask this as a multiple choice because I think it's an explanation. Okay, an impurity affects the melting point. How? What does the impurity do to your melting point? It broadens the range, and that's because we're changing the intermolecular forces within the species. So if we remember back to the lecture, which all of these are posted to, so you can always go back and look at it. If we had a series of boxes as our unknown compound, to hold that together as an individual solid, we'd have all those fun little intermolecular forces in between, right? Well, if we go throw in an impurity, that impurity messes with the intermolecular forces, changing them, which ultimately means we get a broader range because we now have a mixture of intermolecular forces, and I believe you said the other? Lowers it. Okay, that's a standard thing that we've seen, or that you'll see with melting points. It almost always gets lowered. I didn't want that. And that's just because you're weakening the intermolecular forces. It's very, very exceptionally rare to have an impurity increase the strength of the intermolecular forces within a crystal lattice. Okay, because in most cases you're destroying it, making it weaker. Okay, you're looking at 99.9% of the time. Okay. So knowing what impurities do is important, but conversely, what would allow you to believe that it's a pure substance? What would you see with a melting point? You would expect a very narrow range because all of the intermolecular forces are the exact same. So to remove one molecule is the same energy as to remove any other. So once we hit that energy threshold, the whole thing collapses and it turns into a liquid. Okay. What else would we expect? So this is where we got to be careful with the terminology. Okay. So if it's pure, okay, pure, we can fully expect a narrow range. Is that legible? We'll accept that. Okay. But then the next comment, because there's almost always two things that you look for in lab. Okay. Most people will say it, and I yell at people for it. Nothing personal. A higher melting point. It's not a higher melting point. Okay. What we're actually saying is that your melting point, well, we could even say higher if we wanted. You could say it is a melting point that is higher than if it was impure. But if you don't know if it was impure to begin with, you don't really have anything to compare against. So when we're looking at that last thing, it's first off a comparison. It's not just higher, it's higher than something. Okay? And in general, a better way to apply that secondary clause is not so much higher than something, but rather closer to the literature value. Okay? That's really what that second comparison is all about. It's that it's closer to literature value. And if your substance was impure, you're right. It would be lower than the literature value. Okay? But we can't say that higher in general. Does that make sense? It's just not quite specific enough. Does that make sense? Everyone okay with that? So you could get the question as we've got here, which is very direct as far as comparing things. The other option is moving to the other two types of questions, which I don't think I can get on the same page. Nope. Given an actual experimental result. Okay, so in the case from the practice quiz number 1, if you have an unknown sample and we have a melting point, okay, we now want to identify it. So when you see that melting point, what's the very first thing you should think about?
It's range.
It's range, meaning that it's likely a pure sample. Whatever it is pure. Okay? If we then mix that with something else, in this case we decided to mix it with fluoroquinone and vanillin. This is why you attend these things, so you can watch that. That's not very legible. We can then look at their literature values and try and interpret what that would mean as far as our result goes. Okay? So we then take a mixture where we mix it with unknown A, or with known A, and we get a 76 to 83 degree range. What does that mean for our melting point? It's impure. So whatever the unknown was and whatever was in solution A or mixture A were different by definition. That's the only way we could get that lower melting point in our broader range. Okay? We then take mixture B, so in this case it was vanillin, and we run the melting point. We get virtually the exact same melting point. What does that mean about the identity of the unknown?
It's pure. It's the same.
Pure, and it's the same as whatever we mixed in mixture B, which in this case was vanillin. We'd say it's vanilla. Okay. What if the melting point I gave you to start off with, your unknown sample melts between, say, 60 and 70 degrees Celsius? Does it make sense to do any of these 50-50 mixtures?
No.
Why not?
It's impure and it's not going to tell anything.
It's already impure to begin with. Doesn't matter what we mix it with, we're still going to get an impure melting point, which means it makes it very difficult to draw any conclusions from that. Does that make sense? So the idea is to know why you're doing individual steps, because I try to ask questions that push towards those whys. Okay? That's virtually, in fact, that's probably the exact same question. Other things with melting points. So we talked about pure versus impure and experimental results. Pretty much works for melting point. Crystallization. I know that's in here. Guaranteed, without a doubt, this graph is going to show up. You will be asked to interpret this as far as your recrystallization goes. Okay? You absolutely need to understand what this graph means and be able to pull information off of it. Okay? So what I would recommend to start off with as far as interpretation goes would be to put on what I would refer to as the obvious material. Okay? So I would look at this point up at the top of that graph and I would say, what do I know about that point? It's high solubility, which would mean I would just write soluble. Okay? What happens if I move to the very low point? Low solubility or insoluble. Then what do we have for those two? High and low, or hot and cold. Okay? That helps with a lot of the interpretation questions that can come out of this. Okay? So we now have 4 lines on this curve, and it asks which of those is the best solvent for recrystallization. Okay? Well, before we even start off, what makes it best? What do we want for a recrystallization as far as best? We need a variable solubility, which was exactly as you said, high at high, right? And low at low soluble or low temperature. Okay. Once we have that information, we can now go back to our graph and try and find something that matches that. Okay. So if I go to the hot temperature, I now need to find something that's highly soluble. Well, I've got my x-axis nailed down. Now I got to look at my y-axis. Where do I have a high solubility? High up on the graph. So I'm looking at lines A or B. The other part of my analysis was low at low. Okay, so what do I need to do? I need to go through and find where at low temperatures I get low solubility, which means I'm looking at lines B or C. Where's the only place where those two pieces of data intersect? Line B. Okay, so the best solvent relationship here is going to be line B. What if I'd asked a different question? Would like to erase everything, but we won't. What if instead of asking for the ideal recrystallization solvent, I'd asked, let's go, come on, come on. I said I wanted the ideal insoluble impurity. Which one of those represents the ideal insoluble impurity to solvent relationship? Okay. I know you jumped to the answer. If it's ideally insoluble, what does that mean? At all temperatures, it needs to be insoluble. So at high temperatures, it's insoluble. At low temperatures, it's insoluble. So I need to find something that matches all the way across down low. What curve best matches that? C. Okay? So read the question carefully. I cannot explain or stress how important that is, particularly with this question. Okay? Every semester when going through and grading it, people answer the question or answer the problem great for the wrong question. Okay? So read the question, make sure you know what you're being asked. Okay? Which of those curves makes no sense? That one's a little bit harder. We'd be looking at D. Okay? It really doesn't make sense for something to decrease in solubility with temperature. It does happen, but it's very rare. Okay. Why does it seem unlikely for that to occur?
So because usually the molecules will dissolve because as temperature increases the reactivity, that means the temperature of the molecules moving agitation. But
Right idea. You're breaking the intermolecular forces by adding more energy. Okay, so it goes back to intermolecular forces, which we've said again and again and again is important, which you will see on your exam. Did you have a question beyond that? No? Okay. Does that make sense with recrystallization? Okay. Because I'm pretty sure they're on here. Let's go ahead and see if we've got other questions. So practice quiz 1, question 7. You probably would be able to answer those fine, but that was officially from a lab you guys didn't do. So it won't be on there. Practice quiz 3, question 3. Which piece of glassware is required for a microscale crystallization? That comes back to being in the lab and asking questions about glassware, which I won't ask. This question I absolutely would not ask, because what's the answer for question 3 in this case? Anybody know? Nope. Craig tube. Did any of you use the Craig tube for your recrystallization? No. It's an alternate procedure that you guys don't do because it's a pain. Thought there were more recrystallization questions, but I don't see any. Other questions that you could see for recrystallization. You could see some solubility questions, like from the group activity. Since any question I've ever asked you throughout the semester is fair game to ask. Okay, just not. I wouldn't put that very high up on my ranking. I do like this question. Okay, so question 3 from your group activity. Provide a brief method to separate the following mixtures. Okay, the goal of recrystallization was to do what? Purify, separate. Okay, so we might as well be aware of other purification techniques. So if you go through and look at these, maybe it doesn't make sense to do a recrystallization. There's another easier option. Okay? How do you separate water from sand? You filter. Okay? I expect you to know what physical properties water has and what sand has, even though we never worked with either of those. Okay? So there are some questions that I do kind of just assume. Sand from sodium chloride. How do you separate those two? You add water and then filter. So ultimately what you're doing is adding a solvent using the solvent's solubility properties to allow you to separate. You're pretty close to doing a crystallization or a recrystallization. Okay? Being able to interpret the graph to actually put up, it's a good question. It's probably more difficult than I'd want to ask. For sand and sodium chloride, but you should be able to put those two onto this curve. If we looked at water as our solvent, where would we expect sand to be on our curve? Insoluble, which would be very low. There's sand. What would happen if we used sodium chloride? It should be soluble the whole time. Okay? So being able to take data that you're aware of, so sodium chloride is something I expect you to know, sand is something I expect you to know. Your strong acids and bases are a little bit more difficult, but I would expect you to know those as well. If I take HCl and I ask you to dissolve it in sand, where would you put HCl on this curve? How do we typically work with HCl? In a water solution. So if we were going to look at HCl solubility, what would be a reasonable guess? Should be pretty highly soluble. Okay. That's one that I think actually changes downwards, but you don't need to know that. Okay. Yeah, so I would say barring question 4, because that question is a bit more difficult, the second page of the group activity is really good for recrystallization questions. Okay. Questions about recrystallization? Okay. We then did IR spectroscopy. Probably more so than any other experiment, IR spectroscopy should be treated very, very simply. Okay? I will give you a table of where common bonds show up. You just need to be able to interpret pretty much a structure. Since I don't think we've got any questions in here, how do I get a blank page? So for IR, what do I expect? So if I gave you these two compounds versus simple question to ask would be, how do you distinguish these two using IR spectroscopy? What does IR spectroscopy tell you information about? I don't like that answer. There's an easier one. Bonds. Okay. The reason I don't like functional groups is that's a little bit more information than you can pull out of IR, and we'll look at that in just a second. So if I ask you to distinguish between these two, you should go through and generate a list of all of the bonds that you see in each of these. So on the one on the left, we have an OH. What else do we have? We've got a carbon to carbon. I see a carbon to hydrogen. Can you give me more information about that carbon to hydrogen? Not quite. What's the hybridization of that carbon? sp3. Also known as alkanes. What else shows up? Carbon to oxygen. We'd go through and do the same thing on the other side. Give you the easy one first. Carbon double bonded to oxygen. What else do we have? We still have carbon to carbon. What else do we have? Carbon to hydrogen. Can you give me more information about that one? Still sp3. Okay? All you're being asked to do is identify the differences. Okay? Which is one of the things I ask you to do with all of the reactions that we've gone through as well. What's the difference between reactant and product? How do you match those up? Okay? Except in IR, that's where it stops. That's all you got to do, identify the differences. Now what do you do if I throw in the part IR spectroscopy? You look at the table, and you say, what does the table tell you about each of those? Well, it tells you for OH, there's a peak at 3,300, and it's broad. What's the table going to tell you about the carbon-carbon single bond? Doesn't tell you anything about it. So that's not a very useful peak. So we can cross that out. Okay? We could look at the CH bond, since I ran out of space. We'd find out that it would say just under 3,000. The CO probably won't be in the table. It shows up about 1,200. What would you then do? You'd copy the same numbers that you found for the other one, for your carbonyl. You'd say 1,700. CC, we'd see nothing. For the CHSP3, we'd be back at that. If I asked you to tell me the characteristic differences, which of those is going to be important to identifying which compound you've got? And you did all that other work for nothing. Okay? And for nothing, it's important, it's there, it's just not particularly relevant for you distinguishing those two compounds. Does that make sense? So the idea is summarize everything and then go back and find where there's differences. Okay?
So you're saying that is a question that would be on the exam?
Yes. Okay. In two forms. One, what's the difference between the two compounds? Or three forms technically. What signals would you expect to see in the IR? And then bonds. What does IR tell you? It tells you about bonds. So if you gave me functional groups, I'd probably give you partial credit, because it does technically do that too.
Are we going to be provided those?
Yes, or we'll provide you that table. Extraction, probably going to be the most difficult. The most difficult questions on the exam. I would recommend, going through the flow chart from, this is practice exam quiz 2. This will be extremely helpful for identifying things. Okay? If you're familiar with functional groups, that helps out a lot. Okay? As far as your functional groups go, this is one of the things that we talked about briefly in class, but your lecture should have given you a little bit more information on it. That functional group is known as an amine. What do you know about amine reactivity? It's a base. All of you from this morning section should be able to tell me that. What's that functional group? a carboxylic acid, and it reacts as an acid. Sometimes the name gives it away. Okay, so what happens if we take this solution of base acid and then we look at this guy, which is just carbons and hydrogens? What do we have out there? Do carbon and hydrogen bonds react very well? No. And I'm pretty sure, as far as you've seen in lecture, they don't react, which means we would just refer to this one as neutral, okay, or non-reactive. What happens if I add HCl? What's HCl? An acid. What do acids react with? Bases. So I can now set up a reaction between my acid and the base. What do acids do? They donate protons to bases. So what do bases do? They have to accept those protons. What part of that base structure did we say was the base? The NH2. So what happens, and we've got to make sure we find the layers properly, is that I run this reaction. Just going to draw a little circle there. And since I said that nitrogen was my base, instead of having 2 hydrogens, it will now have 3. But in the process, it gained a plus charge. What intermolecular force comes from a plus charge? Or is generated from a plus charge? Plus charges are also known as cation. Ions. What kind of intermolecular force might we expect from an ion? Ionic forces. What kind of compound do we typically classify our ionic compounds by? Salts. What do we know about salts? They're water soluble. Okay? And that's what we're relying on with our extraction technique, is we're changing the structure of our compound so that the intermolecular forces change, which then causes solubility to change. Okay, does that make sense? So it's a question of moving through and classifying and branching these things off as you go through and process it. Okay, what happens in our other layer? Well, that's going to be anything that didn't react or that didn't change its structure when we added the acid. Okay, so both of these compounds should now show up in this layer. So I would just draw those structures again. Okay, so the idea is pace your way through it, do the reaction, and if you need to, draw out the actual equation, the actual reaction equation. That can be extremely helpful for seeing what's going to occur. Okay, and what intermolecular properties change. Do you have questions about the extraction technique? More questions? Okay. Let's see, those are all crystallization, TLC. Don't see any more extractions. Practice quiz 3, the one I'm scanning through very, very fast, which is probably hurting your eyes right now. I think is going to be your best bet for most of the experiments, as far as covering everything. The other quizzes were when we had multiple quizzes in the semester as opposed to just one. Extraction. This was actually your practical. So before we made you answer the question on the quiz. So yeah, as far as extraction goes, you're looking at solubilities in different solvents, either organic or aqueous. If it's water soluble, what's the big red flag that you need to be looking for? So hydrogen bonding we would typically hope to see, but both these compounds have hydrogen bonding. Neither is particularly water soluble. So particularly when it comes to extraction, if we're going to ask water soluble questions, we're not just looking for hydrogen bonding, we're looking for, what's that? Charges. And it doesn't have to be positive, it could be negative. Okay? And in fact, when the acidic compound reacts, benzoic acid reacts with a base, we end up generating our negatively charged species. Looks like it was a 5-year-old. Okay, so if you see an ion, you should immediately be thinking water soluble. Without the ion, organic soluble. Okay, that's pretty much what extraction is going to come down to. Your alkyl halide reactivity. I just saw a bunch of questions on that. You're going to be looking at your SN1 and SN2 reactions. Your sodium iodide and acetone came from your SN2 reactivity. Your ethanol and silver nitrate was your SN1. Okay, so there's some lessons that you were supposed to have learned in those. So this was SN2. This one was SN1. There are a couple big topics that you should remember from both of those, or from that overall lab. Okay, any ideas? What's the most important thing about SN1 chemistry? It's not the most important thing, but that's a repercussion of it. What's that? Stable carbocation. Okay. The very first step in all SN1 reactions is that the leaving group takes the electrons. Which then means what? What happens to the carbon? It's positive in all of those cases. If that carbon cannot stabilize a positive charge, does the leaving group leave? No. Well, if the leaving group never leaves, do you have more than one step? No. Okay? So really your SN1 chemistry is really driven by the stability of the carbocation. Okay? That's really, really, really critical to that reaction working. Okay? If we move to the SN2, what happens there? Don't tell me one step. What's the most important thing? We get backside attack, which, if we want to make that sound really fancy, we say steric hindrance. Okay? The backside of our leaving group leaving has to be accessible. Okay, so we want the least amount of stuff around our leaving group. Okay, so that would be our conclusion for our SN2 reaction. So now we can try and go through and answer the question. Which one do you want to deal with first? 4 or 5? 5. Stable carbocation. What kind of carbocation was formed in question or answer A? So this carbon has the electrons taken away from it, meaning that carbon becomes positively charged. Can you classify that positive charge for me? How many other carbons are attached to it? 1, making that carbocation a primary carbocation. Is a primary carbocation particularly stable? No. And in fact, according to our rules, we would say it never forms. Okay? So if we're looking for it, the fastest reaction, and we get never forms, can't be answer A. What happens when we move to B? Can you classify that carbocation for me? It's a secondary carbocation. Can we form secondaries? Yeah, they're on our list. They aren't the greatest, but they're on our list. What happens here? So I'm hearing secondary, but remember, secondary, our primary, secondary, tertiary classifications only work on sp3 carbons. What's the hybridization of that carbon? sp2. We cannot classify it based on our primary, secondary, tertiary ranking. Okay, so we'll instead classify it by its hybridization, and we're looking at an sp2 carbon. Okay, can we get sp2, or in this case it ends up becomes sp once it becomes the cation? Is that a stable thing to happen? No. Okay, there's all sorts of goofy answers we can go into with that, but it's not necessary to remember any of those. sp2 does not form carbocations. Okay. What's our last case? We're looking at a tertiary carbocation. Tertiary versus secondary, which is more stable? Tertiary, which means D's our answer. Okay? Does it kind of make sense? So the idea is to try and process it as slowly as you can. You do have to know certain things. The SN1 reaction primarily is the stability of the carbocation. Okay? The SN2 is primarily backside attack. So when we look at the backside attack, what would we predict? Particularly because our substrates are now all the same. We still have a primary, secondary, sp2, and tertiary. We end up seeing A react. Okay? Because in that case, the backside of that carbon-chlorine bond is more available. What things are blocking it? We've got that carbon ring and 2 hydrogens. If we look at choice B, there's 2 carbons and a hydrogen. If we look at choice C, there's 2 carbons and we have that pi bond, which has a lot of electron density as well. Okay? And then in choice D, we've got 3 carbons. Okay, so it's coming back to that steric hindrance. What things prevent it from getting in there? Does that make sense? This one's TLC. Really? This one's lame. Oh, practice quiz 2, back on extraction. Question 1 is a good extraction question. It's just looking at those solubilities of those individual compounds. So it's a reformat of the extraction question, but it's ultimately the exact same thing. Okay? So the structures are provided. You just have to interpret where individual things go. Okay? Should we go through that one? Or do you think you guys got it?
We can figure it out, but please tell us real quick.
I can do that. We've got organic, aqueous. How do you determine which layer is on top? Density. It has nothing to do with organic or aqueous. It has everything to do with density. If the density of your compound changes, it's going to change where it shows up. Okay? How would you find out what the density of diethyl ether was? Could try reading the question. The very first sentence tells you that the density of diethyl ether is less than that of water. Okay? I do kind of expect you to know the density for water, but if you asked on the exam, I would tell you. So water is 1 gram per milliliter, just in case. As far as what compounds you should draw here, this question was not very well done. So we'd have to evaluate what's happening in here. We also add NaOH to this solution. NaOH is a strong base. What do bases react with? Acids. What do you think benzoic acid is? Probably an acid. So what happens when those two react? our benzoic acid loses a hydrogen, or H+. So if H+ is removed from the molecule, what would the other piece be charged? Minus. Minus charge is also known as an what? Ion, which means what intermolecular force? Ionic. What's our classic ionic example? NaCl. What do we know about NaCl? Water soluble. What would we expect to see in our bottom layer? We would expect to see that negatively charged species. What would happen to the toluene, which has just carbons and hydrogen bonds, no reaction, stays up in that top organic layer? Okay. Can I close out of that?
Yeah.
Sort of in the interest of time. Oh, already looked at that. That's a TLC. Other big lesson from your alkyl halide reactivity from the SN1, SN2 was the stability of your leaving group. Okay, so if we were going to look at these, which mechanism do you think these would react by first off? SN2, because 50-50 guess? Is that what that was? You're not even going to say yes, huh? SN2, because if we take a look where our leaving group is attached, what can you tell me about that carbon? It only has one carbon attached to it, so these would be primary substrates. Primary would suggest the SN2 mechanism. Okay? Which of these two would react the fastest in an SN2 mechanism? Okay. Well, the very first thing we would do is look at steric hindrance, and we'd say steric hindrance wise, they're both primary, so they'd react the same. Well, it turns out they don't react the same, and that comes down to the stability of your leaving group. At least that's what we're going to say is the answer here, because it's easiest to explain. Which of those is a better leaving group? The bromide is a better leaving group, because why? It's actually not more electronegative, but that's typically a rule we would go by. Okay. Why is electronegativity not as important here?
This one where it's like bigger.
Bromine is bigger. Technically, bromide is bigger. Because it's bigger, it can push that negative charge across a larger area. We're stabilizing the negative charge. Okay. So bromide is a better leaving group in this case.
So how would you know, like at what point in size
When size is important, it's always down a column. Size almost always trumps electronegativity. In fact, I don't think I can come up with an example where that's not the case. Okay? So those are your two primary lessons when it comes to substitution: leaving group ability, and then stability of either your carbocation for the SN1 or steric hindrance for the SN2. What happens if we made this an SN1 reaction? Okay, we could go through and do something like this. Now we could get this to react in an SN1 type of case. Why? Well, let's just erase that and fix it. These both react fairly well under SN1 conditions. Why? Still primary. That carbocation can be stabilized through resonance. It's ultimately the same argument as size. We're pushing the electron density over a larger area. Larger area, more stable. Okay? Which of these two would react faster in an SN1 mechanism? It's a big hint. It's the same answer as you had for the SN2. Okay, bromide because it's bigger. Okay, it can stabilize that negative charge better than chloride. Okay. When we move to alkene, we've got cyclohexanol to the cyclohexene. Okay, so there's a variety of questions that we could ask in here. We could ask the role of the sulfuric acid catalyst. Okay, so what does that catalyst do? Sulfuric acid is what? You could tell me a catalyst, that's fair. What else can it act as? Maybe you said it. It's an acid. What do acids do? Donate H+. Okay? And you're right as far as reacting with the base, but we don't see anything obviously basic here. Okay? So what we're going to do is say, okay, it's a strong acid. It's going to have to give up those hydrogens to something. So it doesn't matter. It didn't have to be a strong base, but it has to somehow act as a base. For it to act as a base, what does it need to do? Accept what? Protons, a positive charge. What kind of species could accept a positive charge? Okay, you're saying oxygen, why? You're right. Because it has the extra lone pairs. For it to act as a base, it has to have electrons to share with the hydrogen. Okay? So what's the very first step of this reaction? We add the acid. The acid protonates the alcohol. Okay? So now what we can go through and do is look at those choices and see if anything makes sense. Okay? Two choices look at protonating. We get A and C. The D and B answers should immediately make no sense because we're looking at an acid deprotonating something. Okay, that doesn't make sense to have a strong acid act as a base under these circumstances. Okay, what does that do to our OH? What charge does the oxygen now become? Positive. It then says our choices are act as a good leaving group or act as a nucleophile. What is a nucleophile? It wants positive charge. Okay, it wants to find a positive. So if it's finding a positive, what charge does it need to be? Negative. Can O positive act as a nucleophile? No, it's the complete opposite of what it needs to be. Okay? If anything, that oxygen has to take electrons from something. Okay? So what ends up happening is it takes the electrons away from our carbon. Our result is that we now have two pieces. What happened? Water left our starting molecule. If water leaves, it becomes a good leaving group. Okay? So be careful parsing together the definitions. This is why knowing what an acid is, a base is, nucleophiles, and electrophiles can become extremely helpful. Okay? Next thing that we could look at was the test for that reaction. We added bromine. Okay? What ended up happening? What's that? It stayed clear. Why did it stay clear? When you added a red solution. Whatever made that red solution was no longer present. Okay? So what you would need to know is that the red solution was bromine, and when we add it to a reaction or a mixture that has a double bond, the bromine reacts with the double bond and is no longer bromine. And in fact becomes bromide. Bromide is colorless, so we see a colorless solution. Okay? So what happens if you added it and it went to that red, yellow, brown color?
It wouldn't have a double bond.
Whatever you added it to didn't have a double bond. Okay? And the bromine stayed in solution. Does that make sense? As far as those other colors go, those came from a different experiment which you guys didn't test, right? You guys didn't do permanganate, right? Okay. So they're there just kind of as confusion as far as you're concerned.
What was this experiment? I can't remember the name of the experiment that was in.
Alkene preparation, or alkene synthesis is what this says, the syllabus. What happens with the 4 alcohols? So now it's asking which will selectively dehydrate to form only one major alkene product. So when you did the elimination, we'll always form the Zaitsev's product. Yes. Okay. Which means what? What is Zaitsev's rule? You form the most stable double bond. What makes a double bond more or less stable? Resonance is a good answer, but if we go through and look at these, are we going to see resonance in any of those cases? No. Why would resonance stabilize? You're ultimately sharing more electrons across a larger area. Okay? So if we look at each of these cases, okay, for instance, that very first one, we could go through and form the bond in several different places. We've got the red alkene, call it the blue alkene, and the green alkene. What's the difference between the red and the blue alkene? They're the same. So we can eliminate one of those as a possibility. Now between the red and the green. Okay, what does the red have around it? We've got a carbon, 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 and hydrogen. Okay. What does the green have around it? Carbon, carbon, hydrogen, and hydrogen. Okay. This explanation is technically incorrect, but I think it works exceptionally well. We're concerned about forming the most stable double bond. Okay. What makes that double bond unstable? If that double bond's going to react, we're going to look at the pi bond coming out and reacting with something. So we're looking at electrons coming out of the structure to react. What do they have to go by in the case of the green double bond? 2 carbons and 2 hydrogens. Carbon's got some electrons, but hydrogen, that doesn't really have anything. Okay? So we're looking at pretty much 2 blocking locations. If we look at the red double bond, it's got 3 carbons and 1 hydrogen. There's one more carbon atom blocking the reactivity of that double bond. Which of those double bonds then becomes more stable? The red one. Okay? It's less able for those electrons to come out and react. Okay? So in this case, we've got 2 possible products, but one of them is favored. The other one is disfavored. Okay? If we looked at, well, selectively dehydrate. So in this case, we end up forming one major product. Okay? For A. The question asks for the alcohol that forms 2 major. So we'd go through and do this same reasoning on each of the other problems. We've got a green double bond and a red double bond. So we go between our leaving group, our OH, and the next atom, or the next position. Is one of those more stable than the other? The green one is more stable, one major product. What happens in the next case? Double bond versus double bond. Which of those is more stable? They're the same. In both cases, we've only got 2 carbons on it and 2 hydrogens. Exact same energy. There is no difference in energy between those two products. So we could say there's two major products for that one. But just for the heck of it, let's make sure we're correct. If we move to this last one, sorry, switch the color. Orange versus green, what's the difference in energy between those two double bonds? Uh-oh. Now we have two answers. It's the same structure. Yeah, they're exactly the same energy because they're the same compound. Both orange and green generate the same product, which means that can't be our answer. We're looking at C.
Trick question.
Okay? Does that kind of make sense?
Can you say again why it's not D?
It's not D because the orange and green double bonds generate the exact same structure. There is no difference between those two products. Okay? It's not even just an energy difference. There's literally no difference between them. Okay? Question 9 and 10. I'm not sure about. We did officially discuss that, I believe, when we looked at IR spectroscopy, that lab. I'm going to have to look closer over your actual group activities to see what things you actually discussed in there and to what level. More than likely, we're going to back away from some of those. So at most, you're looking at probably one question, either cyclohexanes or looking at the relationships between structures. Okay, I'm pretty sure we still covered all that information. Okay, as far as deciding which of these is the most stable form, what's the difference? You're putting the methyl in either the axial or equatorial position. Where should your groups preferentially be? The equatorial position. So we want to go through and find where our methyls are equatorial. And if you want to look at trick questions, this is a good one for it. So here we have axial, axial, axial. How do we know they're axial? Straight up and down. Equatorial, equatorial, equatorial. How do we know those are equatorial? Because they're not straight up and down. Good answer. Equatorial, axial. Whoops. Oh, man. So let's just evaluate those three. I'll change the sizing in a second. So based on that, what would we say our answer is? A is all axial. We want the most stable. Our most stable is equatorial. Axial is the least stable position. Okay. So based on that, we might say B. Except, this is where it's a trick question. What's the question say up at the top? Cis, which is technically an improper usage of the term cis, but cis means all on the same side. If we take a look at answer B, where is this equatorial position aimed? Up or down? Up. Where's this one aimed? Down. Already they aren't all on the same side. B can't be the right answer.
Because it's not that.
Because it's not that name. It's not cis. Okay? So make sure when you answer the questions that you answer the correct question, the question that's actually being asked. This question, because cis is not a nomenclature system that you guys use, I won't ask specifically like this. But you can fully expect a di-substituted situation. Okay? Because there I can get away with saying cis versus trans.
So it's C.
It's either, yeah, it's C. Because D, I think, has two axials. Yeah, D has two axials. Okay. As far as identifying pairs of molecules, for sure at least one of these. I'm pretty sure at least. What's the relationship between these two? How would we figure this out? You need to be familiar with the flowchart that we discussed in recitation, deciding molecular formulas, patterns, all that kind of fun stuff. If they were identical, they would be superimposable. They're not, because this one is dashed going away, this one's wedged coming at you. They're not different, because for them to be different, they have to have different molecular formulas. They have the same formula, so they can't be different. That means they're either structural isomers or stereoisomers. For it to be a structural isomer, it has to have a different arrangement of atoms. Okay? So this is where I would use my weakest skill as far as organic chemistry goes and look at nomenclature. And if I tried to name this, I would say it's 1,2-dimethyl cyclopropane. And I try to name the second compound, and what would I call that one? 1,2-dimethyl cyclopropane. And I wouldn't bring in cis versus trans because that's where the difference shows up. Okay? Which means I came up with the exact same name, which means they can't be structural isomers. Okay? They have the same basic structure, which means they have to be stereoisomers. So structural, you change the numeric orientation of where your groups are in space. So this isn't going to be a good one, but if we'd done something like 1,3-dimethyl, okay, that wouldn't work because they're different numerical arrangement. Does that kind of make sense?
I like that question better than the one before it.
Me too.
It was fun.
I'll take that into consideration. Thin layer chromatography. I'm going to have to defer to saying there's a bunch of questions on that. We've already scanned through a bunch of those. Gas chromatography. I personally hate that lab, so you won't see a lot of questions there. EAS. Which one had it? So there's quite a few EAS questions.
So were you saying that there will not be any gas chromatography? No.
I've got a selection of questions that came from your group activity. You will not see any new original questions on gas chromatography. I definitely do. I haven't even made one version of the exam. There's no way I'm going to write new questions for it. There are quite a few questions on EAS that are in Practice Quiz 3. So I would review those questions because those will be helpful. Okay, identifying again. So we may not have directly asked what a nucleophile is, but in this case, kind of have to know what the nucleophile is in that reaction. Okay, so you'd have to know what a nucleophile is. What is a nucleophile? Nucleus loving, so what does it have to supply? Electrons. So we'd have to go back and have broken down, just like we did in recitation, what each of those species acted as and what did they do. What is the nucleophile in this case? The benzene ring. Okay, that would be A. The role of sulfuric acid and nitric acid is asked in a later question. Down here in the EAS nitration of bromobenzene, a mixture of nitric acid and sulfuric acid were added to bromobenzene. Okay. Anybody remember what question I said was probably going to show up on your final quiz? When we talked about this in recitation? Whoop! There's the death of my computer. That exact question. Okay. It may be formatted slightly differently. In fact, it probably will be to disguise that it's there, but you can fully expect to see that. What is the answer to that question? And I'm afraid to touch anything because I'm afraid it's going to completely die.
Is this like you want Bronson or Lowry?
So if it, oh, it's about to die. Nitric acid we might expect to act as an acid. That's what its name sounds like. But it doesn't act as an acid, it instead acts as a base. So nitric acid in the formation of the nitronium ion, okay, which was our electrophile, acted as a base. Okay? So you might see some level of that question show up. Okay, we went through the mechanism for the formation of the nitronium ion. That could very well be how I asked the question. is drawing it out and saying this is what occurred in this step. Draw in arrows. Okay, so understanding what's happening at each of those stages is important. I really like, what question is that? Question 5, but I probably won't ask that. Just because I don't think we really spent enough time looking at activating versus deactivating groups. It's more of a lecture question. Okay? Yes?
For today's presentation, you said to make sure that we had some of the structures memorized. Is there anything else in particular that we should focus on in today's material?
Intermolecular forces and amino acids. Those are the big ones for protein. I've already had a second request for another review session, so that will probably happen on Friday. I will try my best to get that recorded as well and also posted to YouTube, so you can look at that. The other thing that I'll mention is right now on Blackboard, under course information, that's where all the practice quizzes are. And then there, from the spring semester, I had a student take a picture of the whiteboard that I was using to review all of the labs. So all that lab information was up there. That was the intent for today, but instead of working on that,